we're talking about this diagram here. This diagram, your book called the sub-level energy diagram. This one looks better than the one I posted up earlier, but it's still not the best. What are some problems in this diagram? It's linear. Linear meaning that the energy gaps between all these are the same. Is that what we expect?
No, keeping it shorter.
Right.
Doesn't have the shell like defined there either.
Yeah,
There's some overlap, right?
Right. There's some, it doesn't show like shells at all. Do you see any shells in this?
0 shells.
Yeah, so it's not, if you're going to have to memorize one, might as well memorize one that's a little bit more accurate than this. This is not accurate. And so this is the best one your book has. There are better examples online, but a lot of those examples online are lacking too. So let's go ahead and try to generate this. Another thing I don't like about this figure is the title. It says it's a sub-level energy diagram. Well, that makes sense because it's sub-levels, that's all they're showing. They aren't showing any levels. Levels would be a shell, and a sub-level would be what's in that shell. So the first shell we have 1s, and the second shell we have these two sub-levels, or sub-shells, we call them. It would be the 2s and the 2p. But this just splits it up into sub-levels and treats each sub-level the same. So although some of these will have 3 orbitals, some will have 5 orbitals, some will have 7 orbitals. It doesn't really get into it. And so let's redo this. And rather than calling it a sub-level, we'll just call it, to be more specific, we call it an atomic orbital. Is when I talked about orbitals, there's something called molecular orbitals as well. And those popped up online during the search. And those we haven't gotten to at all. And so we'll put in atomic or just orbital energy level diagram. From what equation was that tells us, what the allowed energies are, what the lowest energy would be? What's the name of that equation? The Schrodinger equation. From the Schrodinger equation, we're going to come out that the lowest energy orbital, an orbital is the answer to the Schrodinger equation, the solution to the Schrodinger equation. The lowest energy orbital will be the 1, 0, 0, or, for short, 1s. And then there's a big jump up to the 2s here. Now, going from the 2s to the 2p, is there a big jump? No, it's a little jump. And the 2s and the 2p have different L's. L's are what we call the angular momentum. So these have different angular momentum. So I like to write the angular momentum separate. So this is L equals 0. This is L equals 1 here. And these would be the 2p orbitals. And then there would be a jump up to the, what comes after 2p? 3s orbital. After the 3s orbital, there's a small jump to the 3p's. So let's group the 3p's over here with the 2p's. And then from the 3p's, we should go to the 3d's, but the 3d's are actually a bit higher. In fact, the 3d's are so high they get into the next shell. And so the next shell comes with the 4s here. It goes 4s and then 3d. So the 3d are higher in energy than the 4s. Not much higher, just a little bit higher in energy. So there's a small jump here, but they're going to be a bit higher in energy than the 3p. And so there are 5 of these 3d orbitals. That's because L is equal to 0 here, L is equal to 1 here. If we have an L equals 0, then the only possible m value is 0. If we have an L equal to 1, then we have 3 possible m values. 1, 0, and minus 1. Those would be the m values. If we have an L equal to 2, how many m values are we going to have possible? 5. Those are 2, 1, 0, minus 1, minus 2. So those are the possible. So we have 5 orbitals here. And then after the 3D come the 4p. How about the 4D? What do you think happened to the 4D? Are the 4D in this shell? No. Actually, it turns out the 4D are in the next shell up. And so what a shell is a group of orbitals with comparable energy here. So here we have the first shell. Here we have the second shell. In the second shell, there are 2 subshells. There's the S subshell and the P subshell. The P subshell consists of 3 orbitals. The S subshell consists of just 1 orbital. And then we go to the third shell. In the third shell, we don't see the 3D. The 3D actually end up in the fourth shell. But in the third shell, we have an S and 3 Ps. When we get up to the fourth shell, here, then we have the 4s, the 3d, and the 4p's. We've got a lot more orbitals in the fourth shell. So I think, what was I talking about last time? The Hund's rule? Did I talk about Hund's rule? No.
Pauli exclusive.
I talked about the Pauli exclusion principle. All right. What the Pauli exclusion principle says is that, what does it say? Maybe I didn't write it down. Did I write it down? No. All right, let's write it down. Oh, wait. The Pauli exclusion principle states that no 2 electrons in the same atom can have the same set of 4 quantum numbers. Did I talk about spin? The 4th quantum number? All right, the 4th quantum number is this. We know the first 3 quantum numbers. The first 3 quantum numbers define an orbital. So let's go ahead and pick one of these orbitals. For example, let's pick this orbital. What would you name this orbital here? The second orbital on 3D. That has an address. What's the 3-number address for this orbital? Each orbital has a 3-number address.
Which one did you point at?
The second one here.
3, 2, 1.
3, 2, 1?
Yeah.
That's correct. This one would be a 3, 2, 1 orbital. 3, 2, 1. So each orbital will have a unique address based on n, which is 3. What's 2? It's L. When L equals 2 is a d orbital, and an m, which is 1. It's a 3, 2, 1 orbital. All right. Then when we put the electron in, there are 2 ways of putting an electron in there. And so when we think about an electron is a spinning charge in the way we think about it, or a moving charge. It's going to generate what we call a magnetic field. Moving charges generate magnetic field. The magnetic field could be up like this. This is called spin up, north pole up. Magnet. I think this is a left-hand rule, so it's spinning like this. Or it could be spin down. So it's either spin up or spin down. So the north pole's pointed up or the north pole's pointed down, that kind of thing. If the north pole's pointed up, we call it plus 1/2. This comes from the Schrodinger equation. And so we don't have a choice. We got to call it plus 1/2 because that's the variable that works there. If it's not plus 1/2, it doesn't work. Or it could be minus 1/2. Minus 1/2 works too. So either plus 1/2 or minus 1/2 works in the Schrodinger equation. And therefore, when we put an electron in here, we usually represent the electron as an arrow. And so an example of this would be like this, the H atom. The H atom, we have our 1s orbital. Another way of saying the 1s orbital, what's this unique 3-number address for a 1s orbital? 100. 100. We could put the electron with its spin up, or we could put the electron with its spin down. And so this would give us quantum numbers for this. The quantum numbers for this would be 100 plus 1/2. The quantum numbers for this would be 100 minus 1/2. And so based on the quantum numbers, we can tell the position of the electron. The position of the electron is given by the first 3 digits. And whether it's spin up or spin down is given by the last digit here. And so this would be N, L, M, S. N, L, M, S. It doesn't matter if it's spin up or spin down. Unless there's some external magnetic field that it interacts with. There is an external magnetic field, the Earth's magnetic field. Now, the Earth's magnetic field is kind of weak, so it doesn't make a huge amount of difference. But if we have a magnet, usually the magnets kind of oppose one another, but it depends on the strength of the interaction. Sometimes it's better if the magnetic fields or moments are parallel with each other versus anti-parallel with each other. In this case, it would try to line up with the Earth's magnetic field. Okay, so that's that. Now, if I try to put a third electron, I could put 2 electrons. But is there a third orientation for this that I could put in? So, for hydrogen, I can either put it spin up or spin down, but there's no other way of doing it. And so what this tells us is that each orbital can hold a max of 2 electrons. Can hold a max of 2 electrons. And those 2 electrons in there cannot be parallel spin. They cannot have the same spin, otherwise that would be a violation of what principle? Each orbital can hold a max of 2 electrons with opposing spin, or anti-parallel spin versus parallel spin. So we want the opposing spin. Because if we had 2 electrons in there with the same spin, then those 2 electrons would have the exact same set of 4 quantum numbers, which would be a violation of the Pauli exclusion principle, or Schrodinger equation, would violate that. As a matter of convenience, when we put the first electron, which one do you think we'll pick? The spin up or the spin down? Just the spin up, just for convenience purposes. And so let's start filling these with electrons. So now, if I have 1 electron in the 1s orbital, this is what I visualize. Do you visualize an orbit, like in Bohr? No. If I have 1 electron in a 1s orbital, what we visualize is something like this. Visualize something like this. Here's the nucleus. And the electron might be here in 1 instant of time. The electron's here. Let's say 1 second later. Do you know where the electron's going to be? No. You can't. That's because of what principle is that? I don't know. I don't know exactly where the electron is because of the famous guy, Heisenberg, right? Heisenberg uncertainty principle. Although, you know, a lot of people think when they think Heisenberg, they think of the TV show. Well, anyway, it could be here, it could be there. And likely it's not very far away because it doesn't have much energy. This is the lowest energy. The lowest energy we call the excited state or the ground state. Ground state. And so eventually what we'll do is we'll just track it over time, and then we're going to get something like this. When the electron's in the lowest energy, you know, we map it out over time, it's going to look like this, and this is what we call the 1s orbital. The 1s orbital, well, we look, well, it's anywhere in there, and so we come up with a boundary, this imaginary boundary called the, this is not, we don't call this boundary a shell, or wall, or barrier. We just call it a probability boundary. And so when we're thinking about an electron in a 1s orbital, this is what we kind of visualize. And pictorially, this is the way we'll represent it. Here's our 1s orbital with the probability boundary here, and the electron's kind of stuck in there. 95% chance the electron's included in this. And the 5% chance is outside of this, so most likely it's in here. Now, if I excite that electron, you know, that is, if I give it more energy, then the electron's going to be more energetic. And so what do you think is going to happen to the boundary? It's going to grow bigger, right? And so if the electron's in a 1s orbital, it's like this. A 2s orbital is just bigger because the electron's got more energy. This is the same shape, though. It's a spherical shape. Or if I go to 2p, it's bigger, but it doesn't have the same shape. It has a different shape. Do you recall what the shape of a 2p orbital is like? Like a figure 8 or a dumbbell shape. It's a 2p. And so it could go to something like that. Here. But normally what we're going to do is we're just going to leave everything in the ground state, the lowest. But of course this electron can get promoted to the second floor, third floor, fourth floor, fifth floor, whatever floor it wants. Within those floors there are subfloors or sublevels. You know, within these levels there are sublevels or subshells. Or within these shells there are subshells. All right, that's hydrogen. Now helium has how many electrons? 2 electrons. And so we want it to be in the ground state, the lowest state, because energy tends to be minimized. Now for helium with 2 electrons, we're going to put the 2 electrons in the 1s orbital. So this would be helium here. So helium has 2 electrons in the 1s orbital. We can get the quantum numbers for both of these. This is a 100 plus 1/2. This is a 100 minus 1/2. That's helium. With helium, look at what we've done. We've completely filled the first shell. And so now if I have another electron, it's got to go into the next shell. Now one of the characteristics of hydrogen is pretty reactive stuff. Is helium very reactive? No, helium's unreactive. Helium doesn't want to react with anything. And so that must mean that this first shell is fairly stable once we fill it. And this is called a duet. When we fill the first shell, we have a duet of electrons, and that's fairly stable. With 1 electron, we don't have a duet. You know, it's just 1 single electron. And so hydrogen has a choice here. Hydrogen can either lose this electron and have no electrons, empty that shell, or hydrogen can take an electron. And it does both. Hydrogen can lose an electron to form hydrogen ion, or hydrogen can gain an electron to form hydride ion. And there are lots of hydrides out there. If hydrogen takes an electron from something, it'll put it in this shell and we'll fill it. Duet. So helium is quite stable, but what about lithium? Lithium has 3 electrons. The third electron's got to go here in the 2s. It doesn't matter if it's spin up or spin down, put it spin up for convenience. So lithium, well, it turns out when we fill these shells, it's pretty stable. But if we look at lithium, it's got this lone electron in the 2s. What can lithium do? If lithium loses 1 electron, then we're just left with this filled shell here. we move on from lithium to beryllium, beryllium has 2 electrons here. So beryllium can lose those 2 electrons, but it's not going to lose these. So once we take these 2 electrons, this shell is stable with the duet. This beryllium, boron. Boron now is going to have a 2p electron. We can pick any of the 2p orbitals. Yeah. And then we go to carbon. With carbon, should we pair the electrons in this orbital, or should we just move it to this orbital? If we move it to this orbital, should it be parallel like this, or should it be anti-parallel like that? You'd think anti-parallel because if you play with magnets, you know, the north likes to line up with the south, but it turns out because of Hund's rule, we fill them up with parallel spins. And so I need to talk about Hund's rule here. Hund's rule states that when we are filling degenerate orbitals, degenerate means the same energy here, energetically degenerate orbitals. When filling degenerate orbitals, fill one at a time with parallel spin. It has to do with the strength of the interaction. When the magnetic interaction is very strong, then it flips anti-parallel. If the magnetic interaction isn't so strong, so if the magnets are farther apart, then parallel turns out to be more stable than anti-parallel. So it depends on the strength of the interaction. So when it gets close, they got to flip. And we'll see that here. These 2 electrons are in the same orbital. But if they're in adjacent orbitals, these 2 electrons are not in the same orbital. If they're in adjacent orbitals, they're going to flip parallel versus anti-parallel. Now, if I took that electron and put it into this orbital, it's got to flip anti-parallel. They're too close. The interaction is too strong. Now, why do they want to go in different orbitals? It's because of not the magnetic. The reason they want to go into separate orbitals is because of the electric interactions. The 2 electrons are both negatively charged. And so they're going to be Coulombic repulsions between the electrons. We call that pairing energy. You know, when we pair it, there's going to be some electrical repulsion because now we have 2 negatively charged particles in the same orbital. Here they're in separate orbitals, so they have a little bit more breathing room. So this is a carbon here, and then we go on to nitrogen. Nitrogen, we put another electron there. And so Hund's rule says fill one at a time with parallel spin. So now we're at nitrogen with. If we go to oxygen, well, what does nitrogen like to do? Let me back up a little bit. Maybe I won't too far. Just back up just a little bit. What does well, we'll go here. Lithium likes to lose 1 electron, correct? Beryllium likes to lose 2 electrons. Boron likes to lose 3 electrons. But when we hit carbon carbon's in a unique position. Because if carbon loses 4 electrons, that's possible, then we'll be left with this filled first shell. The second shell is partially filled. And so we'll see that, for example, in carbon dioxide. In carbon dioxide, the oxidation state of carbon's +4, meaning it's lost 4 electrons. Or carbon's kind of in a unique position because it's midway through this shell. And that is, the other option is carbon can gain 4 electrons. If carbon gains 4 electrons, then we fill up the rest of the orbitals, and we'll have a filled second shell. And so carbon gains 4 electrons, that'd be like methane, you know, methane. It's not that carbon can hold on to those electrons easily. It can't hold on to them easily. And that's why methane's somewhat reactive, but we can see it can gain 4 or it could lose 4. Now, if it gained 5, Sure, it can gain 5, but where would the 5th electron go? The 5th electron would have to go in the next shell, the next energy shell higher, which is unstable. Let's keep putting things in higher energy shells. And so that's carbon gaining 4. 2 here, 1 here, 1 here. Now nitrogen can either lose 5 electrons or it can gain 3. If it gains 3 electrons, then it fills this shell. And having a filled shell turns out to be fairly stable. So nitrogen can gain 3. What can oxygen do? Now we have to pair. And when we pair, there's something called pairing energy, but there's no other way to get around this other than to pair. Oxygen can gain 2, form oxide. And then we go to fluorine. Fluorine will only want to gain 1. And then we go to neon. Neon is special because neon has a filled second shell. And so helium, which is very stable, has a filled first shell. Neon, which is very stable, has a filled second shell. And so neon doesn't want to lose, nor does it want to gain. That's it. So if we do a diagram like this, an orbital energy level diagram, there's a lot of information that we can gain from a diagram like this, but it takes up a lot of space. If you draw diagrams like this, it takes up a lot of room. And so if we don't mind sacrificing some of this information, then we can draw this diagram in a more compact way. In the more compact way, this is called electron configurations. And so with the electron configurations, actually, I need to show this. I'll just start some of these here. The advantage is it takes up a lot less room. The disadvantage is it doesn't show as much information, so we lose some information. So hydrogen has this. It has a 1s orbital with 1 electron in it, so we call it a 1s1, like this. Helium has a 1s orbital, but now it has 2 electrons in it, so we call it a 1s2. Sometimes we abbreviate this because this is a filled shell. And so this symbol here, helium in the square bracket, means that we have the filled shell configuration of helium. And then after helium, we have lithium. Lithium has 2 electrons in the 1s and 1 electron in the 2s. So this is the way we can represent that. 1s2, 2s1. 1s2 is a filled helium shell, so we could use this symbol for that and write 2s1. Like that. That would be for lithium. In fact, the periodic table is kind of arranged like this. When we look at the periodic table, working this morning, but let's show it from here. So hydrogen, we have 1 electron in the 1s orbital. So this is the element hydrogen here, based on the periodic table. Helium, we throw in a second electron in the 1s orbital. So now the 1s orbital, the first shell is filled. So it'd be 1s2. Okay, then we move on to lithium. Lithium starts filling the next shell. The next shell is this. These rows here are called periods. And periods are shells. And so this is the first shell. The second shell consists of 2s and 2p. So lithium has 1 electron in 2s, so we've half filled this shell. If we go on to beryllium, beryllium will fill up this 2s shell. And therefore, we'll have to move on to the next, actually, not shell, subshell. Let's fill up the entire shell means we have to fill up this entire row. So we'll move up to the next subshell, which would be the 2p. The boron would go here with 1 electron in the 2p. Now there are 3 orbitals. 3 orbitals in the 2p. Each orbital has 2 electrons. So boron, carbon, 2. Nitrogen, oxygen makes 4. Chlorine, neon makes 6. Or 3 electrons. I mean 6 electrons with 3 orbitals. So that's the first shell, the second shell. The third shell consists of what? The third shell consists of the 3s and the 3p. And then we jump up to the fourth shell. What does the fourth shell consist of? The fourth shell consists of 4s, 3d, and then 4p. How many d orbitals are there? There are 5 for a total of 10 electrons. So each element adds 1 electron to that. So we've got 10 boxes here. I didn't draw the next shell, but you can tell me what the fifth shell consists of. The fifth shell would consist of 1, 2, 3, 4, 5. This is the fifth shell here. What orbitals will the fifth shell consist of? It will consist of 5s, 4d, and 5p. That's the entire fifth shell right there. Now, the shells have different capacities for electrons. The first shell only has a capacity to hold 2 electrons. We call it duet. The second shell has a capacity to hold how many electrons altogether? 8 electrons altogether. 8 electrons we call an octet. And so neon has an octet of electrons here in this second shell. The third shell can hold a max of 8 electrons. And so that would be an octet. But the fourth shell can hold a maximum of how many electrons? 18 electrons. So those are special numbers. 2 electrons, 8 electrons, 18 electrons are special. There's more. So the fourth shell can hold 18 electrons, the fifth shell can hold 18 electrons, but the sixth shell can hold more than 18 electrons. So what does the sixth shell consist of? When you look at this, the sixth shell should consist of the 6s, the 5d, and the 6p. So it looks like 18 electrons there too, but it's not. It's not because of this periodic table. If we take a look at, this is a regular periodic table, it'll be easier to see. Like this, then you can see something happen. So we call these periods, first period, second period, and we call them shells, first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. Take a look at what happens at the sixth shell. For the sixth shell, we have the 6s, so we need 2 electrons to fill that. Barium will fill it. And then we move on to the 5d here. But look at what happens. The 57th electron goes into the 5d, but where does the 58th electron go? Down here into the 4f. So what they didn't want to do is they didn't want to break apart this periodic table. You know, they'd have to break it apart to stick in the 4f orbitals in here. And so instead what they do is they have a line here directing you down here. You have to insert all these orbitals in here. Now, why do we fill up the 5d and then with just 1 electron and then switch? It turns out that because as you get higher and higher in energy, the orbitals are closer and closer spaced. And so there's very little energy difference between, let's say, the 5D and the 4F. Here. The gap isn't so big. And so here it fills up 1, and then the 58 starts with the cerium, and then goes all the way to lutetium. That's the 71st. Where does the 72nd electron go? 72nd electron is back here, hafnium. And so we start filling this with 1 electron, then boom, we're in the 4F, and we fill those, and then we're back here. And then we complete the 5D, and then go on to the 6P. And so in the 6th shell, now we have the F orbitals. In the 7th shell, it's the same thing. We're going to have the F orbitals here, the 5F orbitals in this case, in that particular shell. Now, these D group elements are called the transition metals. All of these are transition metals. The 4F, do you know what we call the 4F? The 4F elements are called the lanthanides, or the rare earths. The rare earths, like samarium, have you ever seen the samarium magnet? Very powerful magnet. Neodymium, you know, all these are for electronics that are used. So these are the rare earth elements here. The 5F elements are called the actinides. The actinides would be like thorium, uranium, plutonium, curium, californium. All these elements are radioactive. And up to uranium, all of these are beyond uranium are man-made. Anyway, and so this periodic table was originally derived in the 1700s, at least the start of the periodic table. Mendeleev in the 1700s. Is that when quantum theory was developed in the 1700s? No. The quantum theory was developed in the mid-1900s. This one, quantum theory. But we can see, you know, based on orbitals and shells, to be a pretty good fundamental description of the periodic table itself. We can understand some of the properties based on filling these shells or removing electrons to be left with a filled shell. And so once we go past neon, then we go to sodium. Sodium has 1 electron here. And so if sodium is going to react, well, one reaction might be it could lose that electron. If it loses that electron, then we're going to be left with a neon, what we call core. And so this is what we're going to say. You know, this is the helium core here. And so when we look at something like lithium, the core electrons are unreactive. The core electrons, we consider these inner shell electrons. So core are inner shell electrons. Okay, this 2s is just out there, you know, because here we have this core. The core is close to the nucleus, and then we got these 2s. These outer electrons are called valence electrons. These are outer shell electrons. So if you're an oxidizer, you're going to encounter the outer shell electrons, you know, before the inner shell electrons. So if you're an oxidizer, you're going to attack the outer or the valence electrons. And so an oxidizer comes along and it plucks off the 2s electron. Well, that leaves the helium core. The oxidizer might try to attack the helium core, but the helium core is fairly stable. It's a filled shell, and therefore they're pretty unreactive. And so valence electrons are very important because that's where all the chemistry happens. It happens with the valence electrons. So sometimes we just focus on the valence electrons, not the core. So valence, there's another way of defining it. The way of thinking about valence electrons, these are the highest n level whatever the highest n is, the highest n level electrons. So here n is equal to 2. Core electrons, n is equal to 1. So that's lithium. And then let's go on. After lithium comes beryllium. Beryllium is going to be 1s2. This is called electron configuration. Electron configuration is a more compact way of representing this, but it's not as informative as an orbital energy level diagram. So beryllium is going to be 1s2, 2s2, or helium, 2s2. Focusing on the reactive electrons, it's got 2 valence electrons. The 2 electrons in the 2s orbital here. That would be beryllium. And then for boron, we got to go to the 2p. So boron's going to be 1s2, 2s2, 2p1. So this would be helium, 2s2, 2p1. Now, if you're an oxidizer, which one would you take first? Probably the 2p. Pluck that off. Those are higher energy. Higher energy are less stable. Pluck those off. Are you going to stop with the 2p? If you're a hungry oxidizer, would you stop? Because the 2s are more stable, lower energy, harder to pluck off. But how much harder to pluck off are they? Are the 2s like way harder, way more stable than the 2p? Or are they about the same energy? There's not a huge difference. And so if you're an oxidizer, you can take all 3. So we don't distinguish between the 2s and the 2p, because if you're a hungry oxidizer, it doesn't matter. There's not a huge energy difference. And so in this case, we are going to say that this has 3 valence electrons here. 3 valence electrons. And we just group them all together like that. 3 valence. And it's got some core electrons. Carbon. Carbon's going to be 1s2, 2s2, 2p2. And so this will be helium, 2s2, 2p2. For a total of how many valence electrons? Total of 4 valence electrons. So carbon can lose those 4 valence electrons, or it can gain 4 to complete its octet. The nitrogen is going to be 1s2, 2s2, 2p3. So this is going to be helium, 4, 2s2, 2p3, 5 valence electrons here. Oxygen is 1s2, 2s2, 2p4, or helium core, 2s2, 2p4 valence. 2 and 4, 6 total valence electrons. Oxygen. Fluorine's going to be 1s2, 2s2, 2p5, 2p5, which is going to be helium, 2s2, 2p5, which means fluorine has 7 valence electrons. And then finally, neon, to complete this shell, will be 2s2, 1s2, 2s2, 2p6. So this would be helium, 2s2, 2p6. But if we're at 2s2, 2p6, then what have we done to the second shell? The second shell is now completely filled with an octet of electrons, and therefore we're going to call this not helium 2s2, 2p6, we're just going to call it the neon core, quote unquote. And so sodium would just be neon core, 3s1. This is 1 valence electron. Sodium. Okay, let me talk about some other tricky ones. So if we're looking at something like nitrogen, how many valence electrons does nitrogen have? Well, if we fill up the core here, the first shell, the helium, then we're looking at the outer shell. The outermost shell would be the second shell here. And so we're going to have 2s2, 2p1, 2p2, 2p3. So 2 and 3 gives us 5 valence electrons. So nitrogen has 5 valence electrons. How about phosphorus? How many valence electrons does phosphorus have? So we're at, now we're at the neon, not the helium core. So we fill up the first shell and the second shell. This is a stable neon configuration. So we're neon. Then we got 3s2, 3p1, 3p2, 3p3. So 3s2, 3p3 gives us a total of 2 and 3 is 5 electrons. And so we have 5 valence electrons. So nitrogen and phosphorus have 5 valence electrons. Okay, now let's go to arsenic. And so let me write this one on the board. If we go to arsenic, how many electrons does arsenic have? What element number is it? 33. 33 electrons. So the first shell fills up the helium core. The second shell fills up the neon core. The third shell fills up the argon core. And so for something like arsenic, we filled the first shell, the second shell, the third shell are completely filled. So we're going to start from argon here. Argon with 18 electrons. So arsenic, we're starting off with argon that has 18 electrons. Where does the 19th electron go? The 19th electron goes in the fourth shell, starting with 4s. So that's 4s1, 4s2 for the 20th electron. So we fill up that subshell, the 4s2 subshell. After the 4s subshell, then we're going to fill up with the 21st electron, the 3d subshell. And so we go from 21 electrons to 30 electrons, and we completely fill that with 10 electrons. And so arsenic is going to be 4s2, 3d10. And then we're going to go back to the 4p here, the 4p1, 4p2, 4p3. And so this will be 4p3. Okay, so how many valence electrons does arsenic have? 5 is correct. Same number. But what about these 10 electrons here? What do I do with those 10 electrons? If I'm an oxidizer, I want to take the highest energy electron. If I'm an oxidizer, I want to take the highest energy electron because those are the ones that are least stable, the ones easiest to oxidize. And so if I'm an oxidizer, I'm going to come here and I'm going to pluck these 3 electrons first. Boom, boom, boom. And then which electron should I take next? So here we go. I'm going to fill up the third shell. We fill these one at a time with parallel spin. What was that called again? One at a time with parallel spin. Pauli exclusion or Hund's rule? Actually, Hund's rule. What was Pauli exclusion again? Pauli exclusion was. Yeah, in other words, Pauli exclusion tells us the maximum capacity of orbitals. If you want to remember Pauli exclusion, just remember Pauli exclusion principle tells us no more than 2 electrons per orbital. You can't put 3 because it would violate it. And so here we just have 1. 1's fine. And this will violate. So we fill them one at a time, parallel spin, that's Hund's. Now we have to pair it. And so we could put 2 max here, 2 max here, 2 max here. Now we filled it. We're not done yet, because that takes us to argon. So 19th electron goes here, 20th electron goes here. Here, Hund's rule doesn't apply because the 4s is lower in energy than the 3d, and we're doing ground state, so we want to fill the lowest energy orbitals first. That's also that has a name too. You know, the name of that, but I didn't mention the name because there's too many names. The name of that's called the off-bow principle, but forget it. Just fill the lowest energy orbitals first. So I was thinking, should I say the off-bow or should I not? Your book doesn't, so I'm not. So the 4s, we fill that up, and then we go to the 3d. We end up filling the 3d completely, like this. And then we're back to the 4p. 4p1, 4p2, 4p3. So we filled those. Now, if you're an oxidizer, probably these are going to be the easiest pickings here. These are the ones that are least stable, probably most susceptible to attack. The oxidizer comes to attack and take electrons, it's going to want to take the easiest ones to take. Easiest ones. These. So after it takes these three, 1, 2, 3. So arsenic plus 3 is not a problem. In that nomenclature thing in the lab, and this, I don't like it that much. This is why I prefer my handout, but it doesn't matter. In the nomenclature lab in lab, arsenic plus 3 was called arsenus. Remember arsenus? Versus arsenic. Now arsenic gets very confused because the element is called arsenic. But the higher charged ion, like ferric, ferrous, arsenic can mean two things. We're either talking about the element or we're talking about the higher charged arsenic cation. The higher charged arsenic one was, well, the oxidizers pluck these. What are the next highest energy electrons? The 3D. But the oxidizer doesn't touch the 3D. There are two reasons the oxidizer is not going to touch the 3D. The two reasons the oxidizer doesn't touch the 3D, even though those are the highest energy, reason one is because the 3D subshell, we call this subshell, is filled. It's not a full shell, but it's a subshell. And it turns out the 3D subshell is, once it's filled, is fairly stable because of the symmetry of it. You could envision, you know, the 3D being like a cake. You don't want to mess up the cake by taking a slice out of the cake. And so the oxidizer is going to take 4s. But then you go, oh, this is going to mess up the cake. But it's a spherical kind of cake. So even if you take a slice, it's still spherical. So that's orbital is spherical. And so it doesn't mess up the symmetry. That's one reason. The other reason is this. When n is equal to 1, we have the lowest energy. The lowest energy are going to be closest to the nucleus. Right? When we go from n equals 1 to n equals 2, we can think in terms of Bohr orbits. The first Bohr orbit's here. The second Bohr orbit would be 2 times farther out. No, the second Bohr orbit's like 4 times farther out. The orbits go by squares. Well, the orbitals are kind of the same. The first orbitals here, the n equals 2 orbital are like 4 times bigger. Now the n equals 3 orbit is not 3 times farther out, it's actually 9 times farther out. And that means the n equals 3 orbitals are like 9 times bigger than the n equals 1 orbitals. And so when we go to the n equals 4 orbitals, those are like 16 times kind of bigger because it goes by squares. And so this is the other reason why. If you're an oxidizer, you want to take the easiest one to take, and you want to take the ones that are closest to you. The ones that are closest to you are going to be the ones that are the outermost. What's outermost? Even though these are higher energy, which one is farther away? The 4s. The 4s are further out than the 3D. These are like 16 times out, these are like 9 times out. That's one way of thinking about this. And so if you're an oxidizer, you're going to pluck the outermost electron. The outermost electrons will be the 4s. And so the higher, arsenic has 2 charges that are common, +3 and +5. These ones remain untouched because it's a filled subshell. That filled subshell makes it more stable. And so for arsenic, this is what we do. This is called the filling order. We fill it this way. We fill from lowest energy to higher energy. However, as far as it reacting, it reacts differently because we're going to strip the outermost electrons first. And so that means the 3D electrons are closer to the core than the 4s and the 4p. And so sometimes what we'll do is we'll rearrange this to show the removal order versus the filling order. Because if we're going to remove electrons, and the oxidizer is attacking this, and it's going to attack these p electrons first, +3, these s electrons next, +5. But it's not going to touch these d electrons. These d electrons are fairly stable. And so what we're going to call this is not the core. I guess we could call it core. The core are the inner shell electrons. And so the core electrons are going to include 3D. The 3D are inner shell, especially when compared to 4. You know, these are 9 times out, this is 16 times out. And so these would be the valence electrons here. So what we're going to do is we're going to roll the 3D electrons into the inner shell, not the outer shell. And so if you're an oxidizer, what you see are 5 valence electrons, if you're an oxidizer. And so arsenic has 5 valence electrons. Just like phosphorus. What about antimony? Same thing. These 4D are filled, making it stable, and inner shell, making them less susceptible to attack by oxidizers. Same thing. We're going to take a look at some other species here as well. Let's take a look at silver, Ag. Tell me the electron configuration for silver, Ag. Yeah, the easiest.
6-4.
Yeah, we're going to start. If we're looking at Ag, Ag is in which shell? Ag is in the first, second, third, fourth, fifth shell. Ag is in the fifth shell. So we should start with a filled sixth shell, which is krypton. So I'm not gonna build. You can build the shells: first shell, second shell, third shell, fourth shell, fifth shell, and then get to the sixth shell. Or you can just take the shortcut with the electron configuration. The shortcut is I'm just gonna start at krypton. Krypton is the first 6 shells filled. Okay, then that means we just have to work on the first 4 shells. Sorry, first 4 shells filled. That means we have to work just on the 5th shell. Well, you can see the periodic table tells us the shells here, right? And so why do we need to remember all that other stuff? The reason we need to remember all the other stuff is because the electrons can get excited into higher energy shells and higher energy subshells, orbitals, whatever else. And so we got to know what's beyond, we got to know what's beyond the 7th shell. What's beyond the 7th shell? The 8th shell, 9th shell, 10th shell. What orbitals are in the 12th shell? Do you know what orbitals are in the 12th shell? No, but we could figure it out if we sat down. And so this is why we worry about the patterns. Otherwise, we can just look it up on the periodic table. All right, so krypton, let's start off with the fifth shell. The fifth shell is going to start with where? And so krypton takes us to 36. The 37th electron goes 5s. And the 37th and 38th, we will fill that. The 39th electron goes to 4d. So this goes 4d1. Actually, I don't have to worry about this. Because do you see? This goes down here, but this just goes here. And so 39 through the 48th electron goes into the 4d. And so let's fill that up. This is going to be 4d10. Oh, is it? No, I didn't fill it up, did I? I got to go 41, 42, 43, 44, 5, 6, 7, 8, 9. I got 49. So how many valence electrons does silver have? It turns out that does silver have 2 valence electrons? Or does it have 9 valence electrons? If you're an oxidizer, what are you going to pluck? The outermost or the inner? The outermost. What are the outermost electrons? The 5s. And how many electrons are in the 5s? 2. So if you're an oxidizer, you're going to pluck off 2 electrons, giving silver what charge? +2. Is silver +2 observed? Is silver +2 observed? No. No, silver is fixed charged at +1. So there's a serious problem here. What we predict is not what's observed. And so this is what was predicted. What's predicted is, we can just see it here. We'll just put in 2 electrons in the 4s, and then 9 electrons. Oops, this is wrong. Sorry, not the 4s, the 5s. I got to put one more shell in here. All right, so this is the 4th shell. The 1st shell, 2nd shell, 3rd shell, 4th shell, we'll fill it. The 4th shell is going to take us to krypton. And so now we've got to start working on the 5th shell. The 5th shell is going to begin with 5s. And then go to 4d. 1, 2, 3, 4, 5. There are 5 4d orbitals. For a total of 10 electrons. And then from 4d goes to 5p. And do we go higher? Do we go to the 5d next? Or is that the end of the shell? So do we go to the 5d in the 4th shell? No, because the 5d are actually in the 6th shell. Do we go to the 4f in the 5th shell? No, because the 4f are actually in the 6th shell. And so it turns out, well, this is the end of the 5th shell. The end of the 5th shell. So the 4th shell can have a maximum capacity of 18 electrons. The 5th shell also has a maximum capacity of 18 electrons. However, the 6th shell has a higher capacity. You got to add 14 more electrons to that, so it's got 32 electrons that it can hold. So this is the 5th shell. And so the 5th shell, we're looking at silver. And so silver should have 5s2, 4d1, 2, 3, 4, 5. That's 100. 6th half the pair. 7th half the pair. 8th, 9th, we have the pair. And so this is what we predict for silver. But that's not what's observed. What's observed is this. Krypton 5s1 4d10. What happened there? That's what's observed for silver. Silver is observed just to have one valence electron, and that's it. Do you know what happened? Let me tell you what happened. What happened with silver is the energy difference between 5s and 4d is not huge, but it is a jump in energy. And so what happened is this. Nature tries to minimize energy, but sometimes in order to minimize energy, you have to spend some energy. It's like investments or something like that. If you want to make money, you got to spend some money, right? And so let's say you're buying a bicycle pump. You can buy the $5 bicycle pump, or you can buy the $30 bicycle pump, and you might go, okay, I'm going to buy the $5 bicycle pump. Maybe that might be the best decision, or it might be a poor decision. It depends on what. Well, obviously, you go for the $5 bicycle pump versus $30. You save $25, right? But is that the automatic choice? It costs less energy, costs less money. Go for the $5 one.
Maybe it's crap if it breaks right away.
Right. If it breaks right away, then you just wasted $5, right? The $30 might last forever. Well, the same thing. Nature might invest some energy to get a better return on investment. And so what could happen here, and this is what happens, this is the way you think about it, is some energy was invested here. That is, a 5s electron was promoted to the 4d. Why? Because the 4d subshell was only one electron short from filling. And once that's filled, then it becomes much more stable as far as the symmetry goes. And so, silver is observed just to have one valence electron. And the reasoning goes that the s electron was promoted to the d to fill that. And therefore, when we're looking at silver being a reactive chemical, it looks like this. 4d10, this is our core, 5s1. And so if you're an oxidizer, you come along, you attack that 5s, the outermost electron, take it away, and then once you take that 5s electron away, are you going to take more electrons? No, because you got the filled 4d subshell, which is stable. A 4D subshell, the way I like to envision that is like a cake, with no slices. This is perfect. And so an oxidizer, we don't want to take a slice out of that cake. And so silver is called a pseudo group 1. The true group 1 are these, the main group. The main group we label A. So this is a group 1A. Silver is called a group 1B. It's a pseudo group 1. Because silver, like these are the alkali metals, has one valence electron. So this has one valence electron, silver has one valence electron.
It's same for copper, right?
Yeah, this is the same for copper too. So copper does exactly the same thing. What do we predict the electron configuration for copper to be? Copper is going to be AR, 4s2, 3d, 9. This is what we predict, but what's observed is argon, 4s1, 3d10. Or, this is how we fill it, but in terms of reactivity, it's going to be 3d10, 4s1. And so in terms of reactivity, we always go in numerical order, 3, 4, 5, 6. In filling, we mix it up, depending on how we fill it. We'll go from 4 to 3, back to 4, or 6 to 5 to 4 to 5 to 6. You know, when we fill it, it goes like that. But as far as reactivity goes, we want to take the farthest away electrons. And so copper has how many valence electrons? Just 1. And so copper plus 1 is common. Copper plus 1. But copper plus 1 is not the most common state of copper. What is the most common state of copper? Copper plus 2. Copper plus 1 and copper plus 2 both exist. Copper plus 2 is more common. If we have copper plus 2, what must have happened? So the oxidizer comes along and plucks the first electron off, the 4s. That's easy pickings. But to come and take the second electron, it's got to take a slice out of that cake. Well, if it messes up the cake here, then there's got to be some return. And so copper plus 2 has a return. The 3D9 is stabilized by something called ligand fields. But ligand fields is a topic for Chem 1B, so I'm not going to talk about it in this class at all. And so there's a reason for that. But anyway, copper plus 1 exists. There's no problem, so this fits. It's just the D9 is special copper. Gold is the same thing. Gold plus 1 exists. There's also gold plus 3. No reasons for that as well. But let's take a look at zinc. Silver works great. And so if we just think about silver and ignore copper and gold, fine. Just ignore it for now. Zinc and cadmium work great too. What are the charges on zinc and cadmium? Zinc is always plus 2. Always plus 2. What's the electron configuration for zinc? Well, zinc is actually not Kr. Because we have to go back. AR, 4s2, 3d10. And so we'll just rearrange that into numerical or order to get the outermost or valence. So how many valence electrons? 2. The rest are core. And so zinc only has 1 charge. What charge is zinc? Plus 2. And so the alkaline earths like magnesium, these are group 2A. Zinc is called group 2B. It's the pseudo-alkaline earth. 2 valence. Cadmium, what's the charge on cadmium? Plus 2. That would be cadmium. And cadmium would be krypton, 5s2, 3d10. Getting it in terms of core and valence, we'll rearrange it. Inner shell, and then the outer shell will be the highest end. Oh, 4. It should be 4d10. Sorry. And so here we're trying to get a more fundamental picture of what's happening. And this more fundamental picture of what's happening is a theory, and what we're using is quantum theory or quantum mechanics to help us better understand what's going on with these elements here. Well, I passed the break, but you know what I was thinking is, what do you think about this? We skip the break and then maybe get out early instead. Yeah, let's do that. If you guys want to do that. So I'm just going to keep talking and then we'll leave early. Actually, I had the exams yesterday. I was going to pass back, but I forgot to do that. I think I have them today, but I gotta just double check. I brought them. Okay, so electron configurations, normally we just use a periodic table, so we could do something complicated. Like for example, what's the electron configuration for europium? Element number 63. Well, what I do is, okay, 63, what's the nearest noble gas before? It'd be xenon. So I go xenon core, so it's 54. We go up to 55. So I go 6s1, 6s2. And then I go
Oh, weird.
5d1, and then 4f. 4f1, 2, 3, 4, 5, 6, 4f6. And then I'd be done. And so we use the periodic table to get our electron configurations, just based on the shell. Let's see what the shell is for that. So that's writing electron configurations. When we do that, one thing we'll notice is the valence electrons. So let's talk a little bit more about valence electrons here. Section 11.5, valence electrons here. Actually, this is still, exposure is not good. Let me go back to the computer. This kind of, I'm going to blow this up because it's a little bit hard to see there, but group 1A, all of these are going to have valence shell electron configuration NS1. So it'd be 1s1 would be hydrogen, 2s1 would be lithium, 3s1 would be sodium, 4s1 potassium, we're getting 5s1, and they're going to have some core here, except for hydrogen. Now, all these have one valence electron, and we showed that with this. This is called the Lewis symbol. So, for example, sodium would have one dot. Lithium would have one dot. That one dot represents the one valence electron. All the core electrons are contained within here, so we don't show the core electron. If we go to group 2, group 2 would be the alkaline earths, like magnesium. These have two valence electrons in the S subshell. And then aluminum has 2s, 1p. We don't differentiate between the s and the p. The oxidizers are going to take them all. Because there's not that big of a difference between the s and the p, so the oxidizer can easily take them. But first it'll take the p, and then it'll take the s. So we'll take 3 valence electrons. Group 14 or group 4a, the main group is the S block and the P block. The D block we call the transition elements. But anyway, group 14 or 4A all have 4 valence electrons. Group 15 or 5A all have 5 valence electrons. These are the valence. So N is the highest N we have. That's the definition of that. So for phosphorus, we write 5 dots around here. Sulfur, we write 6 dots. Chlorine, 7. Argon has an octet with 8 dots. So this would be equivalent to krypton. Or not krypton. This would be equivalent to argon with brackets. Let's take a look at the size. These are the size of the atoms here. We can use quantum theory to discuss size as well. So let's compare hydrogen. What's hydrogen made up of? Hydrogen is made up of 1 proton and 1 electron. And compared to helium, helium is made up of 2 protons, 2 neutrons, and 2 electrons. Which one's bigger in size? In weight, helium is going to be heavier. Well, heavier, 4 times heavier. But in size, which one's bigger? Hydrogen or helium? Hydrogen's bigger. Hydrogen's bigger, why? Because hydrogen consists of less stuff. So hydrogen has 1 proton and 1 electron. Whereas helium has 2 protons, 2 neutrons, and 2 electrons. Why is helium? Well, actually, let's take a look here. When we look at hydrogen versus helium, which one looks bigger? Helium looks bigger here, doesn't it? Well, that's a printing problem. Because they tell us the radius. The radius of hydrogen is 37. The radius of helium is 31. Helium is smaller. There's a printing issue there. And so the question is why is helium smaller? Why is helium smaller? Helium is smaller because of the greater nuclear charge. If you're an electron and you see +1 versus if you're an electron and you see +2, which one is going to be more attractive? +1 or +2? +2. And so a +2 is going to be actually twice, according to Coulomb's law, twice as attractive. And therefore, it's going to act like a tractor beam, and it's going to pull this electron in closer to the nucleus. And the same thing here. This electron, the 2 electrons try to stay away from each other because they're both negatively charged, so they try not to interfere with each other much, but they can. But if the 2 electrons try to stay away from each other, then the 2 electrons are each individually going to see the +2 charge here, and that's going to make this atom not bigger, it's going to make this atom smaller. It's going to make that atom smaller. And so we see this here. But if we go to lithium, helium has +2, lithium has +3. So if helium's smaller because it's got +2, then lithium's got to be even smaller because it's +3. Is it? No, I mean lithium is a lot bigger. And so what's wrong? Nothing's wrong. It is smaller. That is, the 1s orbital is smaller. And so if we look at the 1s orbital on lithium, this is the 1s orbital on hydrogen, it's this big. The 1s orbital on helium is smaller. The 1s orbital on lithium is going to be the smallest of the 3 because lithium has 3 protons. It's going to pull in the 1s electrons very close and very tight. And so the 1s orbital on lithium is quite small. And so here's how it goes. Hydrogen, helium, lithium. And so lithium has the smallest 1s orbital because of the charge here. But lithium's bigger. Why is it bigger? Because it has another shell on top of that. And so we aren't looking at the 1s orbital anymore. Now we're looking at the 2s orbital. And the 2s orbital is like 4 times bigger than the 1s, right? Something like that. And so now, lithium is bigger not because of the charge, it's because we're adding another shell of electrons on top. And if we add another shell of electrons, then it's going to be bigger. And so this is why we go hydrogen, and then we go to lithium. Lithium has 1 more shell of electrons, therefore it's bigger. And then we go to sodium. Sodium's bigger because it has another shell. And so each of these are growing because of the additional shell of electrons. But if we stay in the same shell, let's stay in the same shell and go from lithium to neon. if we stay in the same shell, then we aren't adding another shell. We're just looking at one shell. And if we're looking at one shell, then what's going to happen is, as we get more and more protons in, then that shell is going to contract smaller and smaller. Just like we saw for the first shell. For the first shell only consists of hydrogen and helium, but helium is going to be smaller because of the more protons. And so lithium has 3 protons, but neon has 10 protons. And those 10 protons are going to pull in the electrons in that shell close to it. But when we go from neon to sodium, well, boom, we got another shell. It's going to be bigger. And so there are 2 factors that impact size. One is if we're in the same shell, it's the number of protons, or Z. So as we go left to right, the size decreases, R, because Z increases. So Z is going to pull in the electrons in that shell closer. As we go down, the size increases because we're adding shells. N increases. And so each additional shell is another N. 6th shell, 7th shell, whatever. And so this is going to tell us the smallest atom. What's the smallest atom on the periodic table? Helium. Helium is the smallest atom on the periodic table. The biggest atom on the periodic table is francium, but francium is radioactive and doesn't last very long, so we'll just ignore it. We'll take the biggest stable atom on the periodic table is cesium. And so here we see cesium. Cesium has a radius of 265. 265 what? Millimeters? Picometers. 265 picometers. Helium has the smallest radius at 31 picometers. That's what we got here. So that's the size trends. And so smallest, top right, biggest, bottom left. And so size decreases as we go up because we're removing shells. As we go up, we're removing shells. Size increases as we go down because we're adding shells. So adding or removing shells. And when we go left and right, going left to right, size decreases because increasing number of protons attract the electrons in that shell more strongly. That's size. Here you can see it. The chart. The next thing we're going to talk about are the ionization energies. Ionization energy, so I wasn't going to use the PowerPoint this chapter, but what and so that was radii. So we're going to look at ionization energy, another application of quantum. Ionization energy is abbreviated IE or I, or E sub I. This is the energy required to remove or take an electron from the gaseous atom. We can take more than one electron. To remove the first electron is called the first ionization energy, so it's IE1. To remove the second electron would be IE2, the third electron, IE3. Depends on how many electrons you want to take away. So this would be the first, the second, the third. It gets harder and harder with each successive ionization. So let's just look at the first ionization, how hard it is to remove just one electron. Here's the ionization process here. Here's the neutral sodium. Sodium is going to have 1s2, 2s2, 2b6, so it's got the filled neon, and then 3s1. To ionize it, we can take the valence electron here. If we remove the valence electron, then we're just left with this neon core. And then one electron goes to the oxidizer. Here are the ionization energies. Basically, when you look at the chart, it boils down to this. Ionization energy is proportional to the radius. It's related to the radius. And so, if the radius, well, think about it. Is it easier to ionize a big atom, or is it easier to ionize a small atom? If you're an oxidizer, is it easier to take an electron off a big atom, or is it easier to take an electron off a small atom? What do you think? A big atom. Why? Yeah, the electron's further away from the nucleus, so the electrical interaction isn't as strong. Coulomb's law says the farther away you're out, the easier. It's like gravity, Is it easier to take an object out further from the center of the Earth, or is it easier to take an object off Earth, closer? Well, anyway, getting to this, so the bigger atoms are the easiest to ionize. The littlest atoms are the hardest. So what's the littlest atom on the periodic table? Helium. So helium should be the hardest to ionize. What's the ionization energy of helium? Well, it's the top. Helium's ionization energy is close to 2,500 kilojoules per mole. What's the easiest atom to ionize? It would be the biggest. What's the biggest atom on the periodic table? Cesium. Cesium's not here. But what we can do is we can use some periodic trends. So potassium's a little bit smaller, sodium's smaller, lithium's the smallest. So lithium's going to be harder, sodium's going to be easier, potassium's going to be easier, cesium's going to be even easier, so it's around here somewhere. Around here somewhere is around the 400 range, right? And so that should be the easiest, 400, around here. And so it just follows the size trends. Hydrogen is bigger than helium. So hydrogen's here, helium's here, so it's harder to ionize. Lithium versus neon. Lithium is bigger than neon. So as we go across, we go lithium to beryllium, it's harder. And then we just keep going. It gets smaller and smaller. As we go smaller and smaller, it's going to get harder and harder to ionize. So sodium to argon. Same deal. The smaller the atom, the harder it is to ionize. Ionization energy is over around here. And so what does it mean? Well, cesium is very easy to ionize. And so like 400 kilojoules is nothing. Whereas helium is extremely difficult to ionize. So 2,500 kilojoules is a lot. It's too much. So helium doesn't really react. Cesium reacts easily. So that's what the energy is. However, it's not perfect. Which one is bigger, which one's smaller? Let's go nitrogen to oxygen. Is oxygen smaller or bigger than nitrogen? Oxygen's smaller. Why is it easier to ionize? Why oxygen's easier to ionize is because of this. There's another factor at play here, and the other factor at play is remember I talked about pairing energy or repulsions? Nitrogen's like this. This is the 2p. And so if I'm going to oxidize this is going to cost me, I'm going to oxidize nitrogen, at least one electron, it's going to cost me this many kilojoules. And so that means I'm going to take one of these 2p electrons. This is for nitrogen. So what's the difference? The difference is oxygen is like this. Now, when I look at oxygen, I have 4 electrons to choose from, but one of those 4 is going to be much easier to take than the others. Which one? Which one do you think is the easiest electron to take? The one that's paired. Why? Because the electrons are both negatively charged. They try to stay away from each other, but they're confined to this orbital, so there's electron-electron repulsions. That's called pairing energy. The pairing energy, well, it can cost you a little bit of energy to pair these. They don't really like each other because of the same charge. Like charges repel. And so because of the pairing energy here, this one is easier to take, so it makes it an exception here. But you don't have to worry about that. Just remember that, the smaller, the harder, with some exceptions. Exceptions based on orbitals. And the same thing with beryllium versus boron. If we look at beryllium versus boron, boron's smaller. If boron's smaller, why is it easier to ionize? It should be harder to ionize a smaller atom. Well, the reason is beryllium is like this. It's 2s2. Whereas boron is like this. 2s2, 2p1. So if an oxidizer comes along, it's going to pluck one of these 2s electrons off beryllium. But if an oxidizer comes along here, which one of these will be the easiest to remove? Well, on the one hand, this one because of pairing energy. On the other hand, this one because it's 2p. It's higher in energy. Turns out it's this one. And so 2p electron's easier to strip off than a 2s electron. And so that's the exception we see here. So 2p is easier to strip off than a 2s. A 3p is easier to strip off than a 3s. So we see it repeated here. A paired electron is easier to strip off than an unpaired electron. A paired electron is easier to strip off than an unpaired electron. So the pattern repeats. And so there's some small exceptions in there that make it a little bit more difficult to describe. So this is what we see. Where's the smallest atom? Top right or bottom left? Top right. What species has the highest ionization energy? Helium. What species has the lowest ionization energy? Cesium. So it just goes by size. The same trend as size. With a few exceptions. Let's skip that. Alright, now they're talking about first, second, and third, but they don't show anything regarding first, second, and third. So I want to show something with first, second, and third ionization energies. Where was that? So here we're going across the shell. This is the same shell, sodium, magnesium, aluminum. So what's happening to the sides? This is the same shell. What's happening with the size is Z is going up, the number of protons, therefore the size is going smaller. So the biggest will be sodium. The smallest in this shell will be argon. And so let's take a look at the ionization energies. This is what we call the first ionization energy, or EI1. It's about 500 kilojoules per mole for sodium. Argon is about 1,500. Argon's smaller, harder to ionize. So, and so 500 is no big deal. It can be ionized. And so we can form sodium plus 1. In fact, that's the most common charge for sodium. But let's try to take a core electron. If we take a core electron, that would be removing a second electron and forming sodium plus 2. It can be done, but it's going to cost you. How much energy will it cost you? This is going to cost you EI1 and EI2. So removing the first electron is 500. Removing the second electron is going to be additional 5,000 kilojoules, roughly. So, well, 5,000 kilojoules, is that a lot of energy? Well, how much did it cost to ionize helium? 2,500. This is twice as much energy. Is helium easy to oxidize? No, helium's a noble gas. It's fairly inert. And so, to form a sodium plus 2 can be done, but you need a powerful oxidizer. Is there something more powerful than fluorine? Because fluorine won't likely do it. You think of an oxidizer more powerful than fluorine? I can think of one with helium. If you take a helium atom and you remove its electrons, what do you have? You have 2 protons and 2 neutrons. In other words, you have the nucleus of a helium atom. And so it's helium with a 2+ charge. Well, taking the first electron is going to cost you a lot of energy, 1,500. Taking the next electron is going to cost you even more, a lot more. That makes this very unstable. But, you know, we don't have to remove the electrons because some radioactive atoms have unstable nucleuses. And these unstable nucleuses break apart. When they break apart, sometimes they'll spit out chunks of nuclei. The chunks of nuclei would be 2 protons and 2 neutrons. Those chunks of nuclei are called alpha particles. And so the nucleus of the helium, an He2+ is known as an alpha particle. This is a different form of radiation. Gamma rays are light radiation, just energy. Alpha particles are particle radiation. These are not waves in the strict sense of waves, even though alpha particles will have wave-like properties. We normally think of them as particles. And so alpha particles, these are more powerful oxidizers than fluorine. And so alpha particles are very, very dangerous because if you think fluorine is nasty, alpha particles are much nastier than fluorine. So if you had high concentrations, it's very dangerous. But fortunately, alpha particles, even though they're extremely dangerous form of radiation, particle radiation, it's easy to protect yourself, you know? Because all you need is like a piece of paper. A piece of paper will block alpha particles. Why? Because alpha particles are such strong oxidizers, they're going to oxidize the paper. The paper is easy to oxidize. Paper is electron rich, easy to burn. So you can protect yourself with a piece of paper from alpha. Can you protect yourself from gamma radiation with a piece of paper? No, it's not going to work. But with alpha particles, no problem. What's that?
For gamma, do you need like concrete or is that?
No, concrete's not enough for gamma. No. Lead apron's not enough. For protection for gamma rays, you need lead bricks. You have to calculate the thickness of lead bricks that you need. You know, usually they sell like 4-inch thick lead bricks that you can use for gamma emitters. Yeah, gamma. You aren't gonna. But you know, you wouldn't look. You'd look pretty ridiculous trying to protect yourself from gamma radiation with a piece of paper. But for alpha radiation, no problem. You can do it. But anyway, yeah, this is going to be very reactive because of the extremely high charge density. Remember the charge density? No. This has extremely high charge. It's because of the chemical reactivity of alpha particles. Alpha particles originate from radioactive elements, but they're chemically very damaging because these are powerful oxidizers. Well, anyway, you need a powerful oxidizer to get sodium into +2. So maybe alpha particles will do it. You know, we need something. Well, for magnesium, we can take away the first electron. It's going to cost us 738, so more energy. Magnesium is harder to oxidize. But we take away the second electron. The second electron is going to cost us about 1,500. And so altogether, we're looking at 2,200. Still less than helium. But if we go on aluminum, what's the most common charge on aluminum? +3. So here's +1, we take that. Here's plus 2, we take that. Here's plus 3, we take that. Now to get aluminum to the plus 3 state, how much energy did it cost? 600 plus 18 is 2400. 2400 plus 2700 is 5100. It's going to cost us 5,000 kilojoules to get aluminum from 0 to plus 3. What's the most common charge of aluminum? Plus 3. How can that be? To get aluminum to plus 3 is going to cost you more than getting helium into plus 1. And helium is a Nobel gas, an inert gas. Even if I had alpha particles, maybe, well, the alpha particles, fluorine will not oxidize helium. Fluorine will not oxidize helium. Maybe alpha particles will oxidize helium. But this is 5,000 kilojoules just to get, well, I don't want to stop at plus 3, I want to go to aluminum plus 4. If I try to go to aluminum plus 4, look at that jump in energy. Why is there such a big jump in energy? Because the first 3 electrons are valence electrons. The 4th electron would be a core. So we're going to upset or ruin the core. And so this is the dividing line. The blue is valence, and the pink is the core. Now, here, why is that? It doesn't make sense. This doesn't make sense. This doesn't make sense because to form the aluminum 3 plus costs 5,000 kilojoules. To form helium plus costs 2,500, half as much energy. And so why isn't helium plus a common ion? Aluminum 3 plus is the most common. In fact, do you find aluminum metal in nature? No, because all the aluminum is aluminum 3 plus. You know, aluminum metal used to be a rare and valuable metal. Now it's cheap and plentiful. What changed? No, it's always been mined. It's mined from bauxite, which is very common. Aluminum ore is very common. You know what? What's changed is how they refine it. Aluminum forms, are we out of time? No, or almost? What time do we end today? 4:30? We didn't take a break, so we're ending early, so I'm going to cut it. We cut it now? Aluminum ore is this. Al2O3. Aluminum oxide. That's aluminum ore. And the situation with aluminum ore is the bonds are so strong. It's so difficult to get this to react. In fact, I used to use aluminum oxide cookware all the time for my cooking and chemistry. You know, I had a catalog of cookware, it's boats and crucibles and whatnot. And so I had all these aluminum oxide ceramic dishes. They're really expensive, but you know, you could heat them up to extreme temperatures, like 1200 degrees C with lots of reactive chemicals in there, and nothing happens. They're untouched because this stuff is so unreactive. Why is this stuff so unreactive? Because the bonds are so strong. You know, you got a 3 plus cation and 2 minus anions. They're strong bonds. And so, to make a long story short, it was so expensive to get this stuff to react. Therefore, aluminum metal was very, very expensive and very rare. And then finally, somebody figured out how to get this stuff to react cheaply, you know, to break the bonds in there. But anyway, so the reason is yes, this costs more energy, but what you get in return is something very stable. And so you have to look at the long picture. You know, you don't look at the short-term picture, but you look at what's at the end. What's at the end is you're going to form a compound that's going to have strong bonds. Whereas if helium plus, yeah, it costs you less energy, but it's only a +1, not a +3. You aren't going to get nearly as strong a bond. And so the cost versus the benefit is lower, even though the initial cost is lower. Does that make sense? This happens in nature all the time. And so there might be a larger initial cost, but the final cost is going to be favorable. Well, anyway, I'll stop here because I said I was going to end early. So I'm think I'm pretty sure yesterday I had the exams, and I was just looking in my bag, and I was glad I had the exams. Let's see.